All right, let's get started. Any doubts from the previous week content? Limits and continuity? Okay. If not, then let's get going with week 8 stuff. We'll quickly recap what we discussed over there in the context of continuity, and then we'll go into derivatives and some phenomena which arise as a consequence. So if you remember what we discussed, take a quick overview of what we had last. The idea was to get the graph of the function and derive certain properties. One thing that we thought was desirable was for the graph to not have breaks. So in order to make this notion rigid or rigorous, we define limits initially of sequence of real numbers we loosely put it down as an converges to a if an approaches or gets close to a as n increases. And then we saw many properties of limits. And using the notion of what the limit of a sequence is, we defined limit of a function at the point A. And how was that defined? Left-hand limit of f at A exists if important to note that this has to happen for every sequence. For every sequence an less than A and an converging to A, we have f of an converges to some real number L. And that L is called the left-hand limit of f. And the notation is L is equal to limit as x approaches a minus f of x. A minus meaning we are looking at points which are to the left of L, meaning on the, if you suppose take the graph of a function, let's take something this, and suppose I'm interested at x is equal to 0, I look at points on the x-axis, sequences on the x-axis, which approach the point 0 from the left, and I look at corresponding function values. In this case, they happen to approach the point. Okay, suppose this is at height 1. They approach 1, right? But this need not always be the case that they approach to the function value at that point. We have seen examples like the floor function. The same concept for similar concept definition for right hand. I'll abbreviate it as RHL. Now to see why left-hand limit and right-hand limit need not be the same. Consider f of x is equal to floor function of x. The limit doesn't even need to exist, as we have seen in numerous examples in the solve with us session. So what is floor function? At 0, it is 0. I'm not drawing the negative side. Up until 1, it is just that. And then it jumps. At 1, it jumps. And until 2, it remains the same. And so on. Now, what happens to what is the left-hand limit of f at, let's say, x is equal to 1? Does the left-hand limit exist? If it does, what is it equal to?
Left hand limit at 1
1.
would be 1.
Yeah. So it exists limit as x approaches 1 from the left. So this is x is equal to 1. So if I approach this point from the left, the function value approaches 1 itself, because at any point on the left of 1, the function value is identically equal to 0. Sorry. Yeah. It's this is equal to 0. So why did you guys say 1?
Because the 1 is you have marked it like circled it.
So f of 1 is 1. That is okay. But what is the left-hand limit of f at x equal to 1? To understand what the left-hand limit of f at x equal to 1 is, you have to look at points strictly to the left of 1. Let's say you take something like 0.9, 0.99, 0.999, so on. Okay, so at 0.9, what is the value of the function?
0.
Right? At 0.99 also it is 0. So
0.
even as you can go as close as you want to the value x is equal to 1. From the left, you will always be the corresponding function value will always be 0. So the limit of the function as you approach 1 is actually equal to 0. But what about the right hand limit?
Right hand limit means once you pass 1, it becomes 1.
Yeah, so you're approaching from this side. You're
It becomes
approaching
1.
from this side. So corresponding function values, similar table, if drawing such a table helps, you can take 1.1, 1.01, 1.001, and so on. You can take smaller and smaller values. But irrespective of what you do, here the function value will be 1 itself. Right, so this also exists, and limit as x approaches 1 from the positive direction is equal to 1. So in this case, LHL is not equal to RHL. So if left-hand limit and right-hand limit are equal, then the function is said to have a limit at that point. That is the definition of limit. And for continuity, you will have f is continuous at x equal to a if the left-hand limit of f at a is equal to the right-hand limit of f at a, and this also happens to be the function value. Is it clear why this is 0?
Yes.
Okay. So in this case, is this a continuous function, the floor function?
No, sir.
At
No,
what points do we have a problem?
at 1, it's not
At
continuous.
1. And similarly at 2 and so on.
Yeah, so at integer points, you have discontinuity. And
Yes.
what about other points? Suppose you take something like 0.5.
No, in
Is the function
non-integer,
continuous at
it's
that point?
continuous. Yes.
Yes, sir.
Yeah, because in a small neighborhood, you will have the function to be a constant function. Small neighborhood meaning some interval around that point. So whenever you're taking the limits, all you're worried about is very close by points. So if you're looking at continuity at x naught, for example, you look at very small intervals of this form or very small epsilon. You have to first approach x naught from this side, and then you have to approach x naught from the other side, and then analyze the behavior of the function. And if both of the function values tend or approach the same point, and that also happens to be the function value at that point, then it is said to be continuous. Now, can you give me an example of a function for which right hand limit and left hand limit both exist and they are equal, but the function value is not equal to those two things?
Sorry, I didn't realize I was. So fx is equal to x when it's less than 0.
So this is not an example of a continuous function, but yeah, let's write it down. Fx is equal to, could you repeat, please?
Fx is equal to x when it's less than 0.
X is less than 0. Okay.
So I have to give an example of a function which is not differentiable, though it's continuous, right?
No, I want RHL is equal to LHL, but
Mhm.
f of A is not equal to either of those. Let's say RH.
Okay. In that case, say,
Sir, you can take x square when x is not equal to 0
yes,
and
x square
some
plus.
non-zero value when x is equal to 0.
If you draw the graph of this function, what would it look like? It would look mostly like f of x is equal to x square. So the obvious problem at the origin, you will not have this value, but instead you will have a jump is equal to 1. So clearly this is not continuous, but the function
Or
approaches
the
0.
example I was giving, like fx is equal to x when it's less than 0, and fx is equal to x square plus 1 when it's more than 0.
X less than 0, x square plus 1, is it?
Yes.
This one would not qualify for this class because what we can
RHL
argue
equal
algebraically
to
also.
f of 0 here.
So here f of x or less than 0, it would be the straight line, and then x square plus 1, it would be something like this, including this point, excluding this point. Here the right hand limit and the left hand limit are not equal. No, the left hand limit is 0 and the right hand limit is 1, which also happens to be the function value at that point.
So
Right?
LHL is not equal to RHL.
I want it equal to RHL, but not the function.
Okay.
So such things also can happen. So how can discontinuity happen? Either of right hand limit or left hand limit does not exist. If that is the case, then limit obviously does not exist. And then if both of them exist, they can be not equal. And in that case, your function is not continuous. If both of them are equal, they might not be equal to the function value. In that case, also it's discontinuous. So for continuity, you require both the limits to exist, to be equal, and to be equal to the function value at that point. All right, so this is about continuity. And we can formulate continuity in terms of sequences as well. If you take any sequence converging to the point of interest, the corresponding function sequence should correspond to converge to f of that. But this is easier to understand, so we'll leave it at
So
that.
can you explain that example that you just showed, the x square one? Just the
This one,
yes, yes, yes.
this one is it?
The yes, sir.
Okay, so what do you need clarification on?
I get it that it's not continuous by just looking at the graph, but
Right.
the FA not equal to RHL because
So what do you mean by limit as x approaches 0 minus or 0 from the left of f of x? To the
yeah,
left of f of x, what is
Hmm.
the value of the function?
it's
It is simply x square.
yes, sir, correct.
So what does the function x square approach as you approach 0 from negative side?
It goes to 0, but then there is
Yeah.
a jump at 1.
So when I'm looking at the limit as x approaches 0 of a function, I do not care
Yes,
about
sir.
what is happening exactly at that point. I'm caring only strictly to the left of that point for the left hand limit. So it does not matter to me for in the context of the computation of the limit at that point, it does not matter to me what the value at that point is. So
Right.
I am only looking at x square, which is the behavior of the function strictly to the left of it. And the value of this expression x square as x approaches 0, that is actually
Yes.
equal to 0.
Yes, sir.
Now, you should kind of forget that f of 0 is actually 1, but because that is not what we are asking for. When I'm asking what the right hand limit is now, again, what I will look at is strictly to the right of the
Right,
function, right of 0, the function value. Once again, it becomes x square. And
Yes.
this expression x square, as I approach 0 from the right, it approaches
It also goes to
0
0.
itself.
Yes, correct, correct.
So this is LHL, this is RHL,
And this is
both of them exist.
correct.
And
Got it, sir. Got it.
they are equal, but
Yeah,
as it so
it
happens,
does not equal.
f of 0 is not equal to LHL or
It's not equal
RHL.
to. Got it, got it. Yes, sir. Thank you so much.
Okay, so just for maybe for one more clarification, consider the following function. This is also called signum function. Without drawing the graph, first we'll try to do this. This is not an example with this requirement, with the requirement that the limits are equal. Just to understand how to compute limits, if you know the expression to be one way on either side, and at the point it is something else. So can someone tell me what the left hand limit is? Can you guys quickly compute and let me know?
It is -1.
There is a claim that it is -1. Does everyone agree that it is -1?
I can't understand. Could you please repeat it? How -1? I think 0.
Okay, first let us not draw the graph and let us just write it as we usually do. Left hand limit at x equal to 0 is -1 is the claim. Let's see. So limit as I approach x from the negative side, approach 0 from the negative side of f of x is what I want. But to the left of 0, what is the behavior of f of x? In fact, for any point other than x equal to 0, what is the definition of x? What is the definition of f of x? It is just x by mod x. But what is x by mod x for negative values of x? Because we are on the left now.
X by minus x.
It'll be positive.
X by mod x will not be positive.
No, yeah,
Let's-
the downside will be, yeah, x could be negative. So, yeah.
Yeah, mod x would come as negative.
So this will become -1. Well, that's one step further. Limit as x goes to 0 minus of this function -1. But this function is a constant function.
Yes, sir.
What is the limit of the constant function? It is just that constant itself.
Yes.
On the other hand, if I want to do the right hand limit, I would try to approach 0 from the positive side. Once again, the same thing happens. But in this case, due to the way modulus function is defined, on the right side, what is the difference that would happen? The denominator would not be minus x, it would just be x. So this is just 1. So the right hand limit is +1. So in this case, what has happened is left hand limit, right hand limit, both of them exist. Both of them are unequal. And the function value is something else altogether. F of 0 is 0. Now consider this function, g of x, which I just write as -1 if x is less than 0, 0 if x is equal to 0, 1 if x is greater than 0. Do you see that f and g are the same?
Yes.
Yes, sir.
Right?
Yes.
Now, if it was not written in this form, if you were given g, would you be more comfortable with the computation of the left hand limit and right hand limit? Probably. And if you want to draw the graph of it, either of them, because both of them are the same, so we can just take one of them and try to draw the graph. A straight line, which means it's a constant function, all the way until 0. And this straight line is at a level y is equal to -1. At 0, it is 0. And on the positive side, it is constant 1. This is the graph of the function. If you drew the graph of the function, of course, this would be clear that as I approach the point x is equal to 0, from the right side, I would approach 1 because everything is 1. So if I take 1.1, 1.01, whatever greater than, 0.1, 0.01, whatever sequence of points that I take, the function value is identically 1. So the limiting value is also 1. So this is something that you have to,
That will be 1.
sorry,
Even if we take as 3 or 2, then
see, you have to take a sequence which converges to 0 because you're interested in continuity at 0. So something of
so
the
at
form,
x is equal to 3. So in
the function is
x-axis-
continuous at x equal to 3. Is that your doubt?
No. X is equal to 3, limit would be 1.
Limit would be 1. Yeah, limit would be 1. The function value is 1.
Yeah.
Are you saying that this? Are you asking if this is true?
Yes.
This is correct, but this is not interesting. We are looking at the behavior of the function at x equal to 0 in just for this problem. But that was a correct statement. For left hand limit, you are looking at this side of the graph. For right hand limit, you are looking at this side of the graph. All right. So is this clear why this is this way? The computations, left hand limit, right hand limit, and the function value, all of these are different values. Is that fine?
Yes. Yes. And so g of x is basically the same thing as f of x here, right?
Yeah, f is equal to g.
But in the previous function, which is a parabola, I see.
Uh-huh.
Yeah, this one, which you have drawn. So this is continuous now. So LHL is becoming is equal to RHL. So this is
LHL is
continuous.
equal to RHL is satisfied, but deliberately we have defined it differently at the point x equal to 1. Sorry, x equal to 0. We have given it the value 1. If
Yeah, that is
so for continuity, you need both of those limits to be equal to the function value as well.
Yeah. LHL also.
So I'm just demonstrating in different ways in which continuity can fail to work. Okay, you should be able to come up with examples of any way in which continuity fails. Right? Now I'll list down some properties of limits, things you probably already know and you already use. Suppose I have f and g from certain domain. I'll not write down all the details. F and g are one variable functions defined in a neighborhood of zero, in a neighborhood of defined in a domain. I'm going to write containing A, and this is actually not strictly required, but don't worry too much about that. Containing A and limit as x approaches A, this limit as x approaches A, g of x. It's this. Now there are some rules, things you would expect. If I look at the sum of two functions, you subconsciously apply these things without thinking too much about it. Let's try plus g. The limit of the sum function is the sum of the limits. The limit of a scalar multiple of the function is the scalar multiple of the limit, and then the product limit of the product is product of the limits, and then limit of the quotient. Of x f by j of x is this, but here, of course, you need g to be not equal to the limit of g to be not equal to 0. This would guarantee that in a neighborhood, for nearby points, it is non-zero, and everything works well. Whenever you have quotients, you make sure that the denominator is not vanishing. Now, there is a sandwich principle for sandwich lemma for limits as well. For limits of sequences, we have already seen this. This is there for functions also. If limit as x goes to a f of x is equal to limit as x goes to a g of x is equal to, let's say, L. And h is a function which is sandwiched between f and g. Then the limit of h also exists and is equal to the same L. As is the usual way, it is better to understand with an example. What is limit as x goes to 0, x sine 1 by x? First, what about just sine 1 by x? What is the value of this limit?
It's between -1 and 1.
Does the limit exist?
No, sir.
Yeah, we have seen this in the solve session, that this limit does not exist because it keeps oscillating between -1 and 1 infinitely many times. As you approach, there's no one fixed value that the sine function approaches. But as soon as I multiply it by this, now there is one caution that I have to tell you about. Look at this product formula. So here I have product of the function x and sine 1 by x. I cannot write it as this using the product rule. This is a wrong step. Why? Because this limit does not exist. Only when both the limits exist can you write it as a product of the limits. All right, so this would be 0 times something undefined. So is the limit, does the limit of the product not exist? Individually, the functions may not have limits, but still the product can have a limit. So this is an example which shows that. So I cannot use the product rule really, because the one of the components of the product does not have a limit. But what I can do is sandwich lemma. So so suppose this is my function h of x. What can I write as the two extreme points of h of x? Irrespective of what
-1
x.
and 1.
H of x is not between -1 and 1.
Oh, okay. So,
Let's take this. What do we know about this?
this we can say that it is between -1 and 1.
Right?
Yes, sir.
Now for x positive. So if I want to say that this limit exists, I have to tell you both left-hand limit as well as right-hand limit. First, let us do right-hand limit. For right-hand limit, if I multiply this inequality by x throughout, what will I get?
0.
No, just multiply it by x.
Minus
Will I
one.
not get this?
Yes, sir.
Right? This one. Yeah. Now, what is the limit of this function as x goes to 0?
0.
And what is the limit of the other function as x approaches from the 0 from the positive
Same.
side? That is also 0.
0. Yes.
So what we have done is we have sandwiched the given function. We have to calculate the limit of some function. We have written it in between two functions, both of which converge to 0. So the sandwich lemma says that this implies by sandwich lemma limit as x goes to 0 plus x sine 1 by x is equal to 0. So if you have two functions with the same limits and your function h can be written to be both of the functions are such that h is always in between f and g, then h also converges and to the same limit. That is the sandwich lemma. Is this clear? Is this example clear?
Yes, sir. Can I just confirm one thing? The
Yeah.
part where you said that the individual element does not have a limit. That is the part, or the sine 1 by x part, right?
Yeah. So you cannot always say that this is equal to this. So this seems to
Yes.
contradict what I said earlier, right? So here I've said that this happens, but here I'm saying that this does not happen. But here we have assumed that these limit exists. If the individual limit
Both.
exists, both limits exist, then the product also limit exists and is equal to the product of the limits. But if you don't know if these individually exist, then you can't make this statement.
Yes, sir. Got it.
It
So
would
sine 1 by
not
x
make
is
sense,
not
right?
existing because
Yeah.
as x goes to 0, it becomes non like it does
Okay,
not
I
exist, right? Because x
Yeah.
goes to 0, the denominator comes.
It keeps continuously oscillating. So as x goes to infinity, sine x doesn't really approach something. So
Yes.
contrast this with e to the x or e to the minus x. If you have e to
Oh,
the
okay.
minus
So we
x,
would
it is something
calculate.
like this.
Oh,
So here,
no,
limit
so we
as x goes to infinity, e to the x is actually 0. But sin x does not, right? Sin x does not go to infinity, go to any value as we increase the value. But here, what we are taking is x goes to 0 sine 1 by x, which is just another way of writing the same. And as x goes to 0, 1 by x goes to infinity. And
right,
the sign of that does not really approach any one particular.
right. Got it. Okay.
And
just a question,
yeah,
which is coming in my mind. So we have x into sine x 1 by x. Okay. So can we divide and multiply by 1 by x?
okay, you would get sine 1 by x by 1 by x.
By 1 by x. And then x
If
multiply
x
by 1
tends
by
to
x.
infinity, then it would be 1. But here x tends to 0.
Acha, 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 acha.
So, but the
Okay,
part where um, we checked for the individual limits, we are checking for as x goes to infinity or as x goes to 0.
As x goes to 0, but by the why I said x goes to infinity is I was just looking at the behavior of sine x as x goes to infinity.
Hmm.
But here we want sine 1 by x as x goes to 0.
Yes, sir.
So as x goes to 0, 1 by x goes to infinity, right? So that's why I looked at this behavior.
Okay, got it.
Yeah. Shall we move on?
Yes, sir.
All right. So this was about the properties of limits. The properties of limits you will keep using to calculate many limits. There's one more rule for limits which will come only after derivatives that will be covered in this session as well. Some trivial examples, if you want, you can take polynomials. AI, xi, I going from 0 to, let's say it's an n degree polynomial. If you want to compute the limit of this, and if you really want to give a proof of why this is actually equal to just substitution, you can see that limit as x goes to x naught of the monomial x is actually just x naught. And then you can multiple times use product rule, scalar multiple, and sum, and then you can just say that this is the value, just evaluating it at this point. It seems like something that would not require a proof, but if you really want to be pedantic and give a proper proof, this you can. If you want. So that is that. If necessary, we'll come back to examples a bit later. There are some limits that you need to have in memory. Things like take it as a fact, not question it. It is not too hard to prove this properly, but we are not going to do it. This and then things like
So I was trying to convert the previous question into this form, sine x by x.
yeah, I realized that. So, but then your x needs to go to infinity for that. right? So you can't get it in this form. Because if you get it in this form, then it would become 1, but that's not the answer even. The answer is 0. Right? So if Vx minus 1 divided by x is 1, as x goes to 0, you have stuff like log meaning natural log. This is also
Another question in the quiz, will this expression be already provided in the paper?
no, but sin x by x. So after L'Hopital's rule, all these things will be obvious. There will be something that you need to commit to memory, either derivatives of some standard functions, which I think you already know. I'm assuming everyone has seen derivatives in some form beforehand. Is there anyone who has not seen derivatives at all and will be looking at it here for the first time? No, right? So I'm assuming you know that the derivative of sine is cos, cos is minus sine, log is 1 by x,
Yes,
x
sir.
to the n is n times x to the n minus 1. All of these things, even if you don't know, you can derive all of it using the things that we are going to explain. But if you know all of these things beforehand, it will be very helpful. I will not. Sorry, I couldn't hear you.
I said know the derivative.
You know the derivatives, right?
Yes.
Even if not the geometric meaning of the derivative, I'm assuming you have had some familiarity with using it to do math problems in 11th, 12th, wherever, at the very least. Right. So that these are some of the limits that you need to know.
Sir, in exam, if some question based on these limits, will it be given in the question?
So I'll come back to this question once we get done with the session, because then it is easy. So I'll tell you why it is easy. All of these things that you need to commit to memory right now, if you know derivatives. So I would say remember derivatives, which is due to doing lots of problems you will already know, and then all these things will become easy. This will make sense later. I'll talk about it.
Okay, sir.
So that is about limits. I think that's where we'll stop with limits. Next, we'll go to differentiability. Now, why did we even start with the limits? Continuity, sequences, nearby points thing. We were looking at when the graph of a function is nice and it's smooth. It's a curve. So one of the classical examples for something that is not curved was the modulus function. This function looks roughly like this, right? Now, even though the function is continuous, this is f of x is equal to log x, we see that it has a corner, and we cannot define, we cannot have a well-defined notion of the direction that the graph is going in at the point x equal to 0. So if I take any other point, I know that the graph is going in this direction. The function is headed in, is inclined at a certain direction. But at 0, I can't, because on the one hand, before 0, it is headed in this direction, and after 0, it's headed in this direction. So at 0, I can't, and the change is abrupt. Even though the function change is not there is no break, the direction in which the function is going has a jump. Even if that doesn't make sense to you right now, that's fine. But you can see that it has a corner, right? So we need something more than continuity. to do calculus where you measure instantaneous rates of change. So if you are looking at something called rate of change, things like this should be avoided. So what is the rate of change of a function? So let us first give the idea of the derivative. When you say derivative, you should think of it as rate of change of idea of the derivative of f. I'll just write it as idea of the derivative is rate of change. Now, the most common example that I know of for rate of change is that of speed. Speed is the rate of change of what? How would I complete this sentence?
Distance.
It's the rate of change of distance. So to see this, so if I start at t is equal to 0 and at t is equal to 10, if I have covered 100 meters, let's say, what is my speed? Average speed.
That is 100 by 10.
So this is
10
an
meters.
average of 10 meters per second. But this would not tell me that at every point I'm moving at 10. There might be some places where I moved at a slower pace or a faster pace. So this is an average. Now, if I want to know instantaneous speed, what does instantaneous speed even mean? So suppose I draw the graph of my, I draw the graph of distance against time. I'll write this as the t. This is the x-axis, but we'll call it the t-axis for purpose of this. So suppose I started distance 0, and let's say at t is equal to 4, I have reached something like 50 meters, and I have done it in a linear fashion. So for example, at t is equal to 2, I was at 25 meters from my starting point. And then at t is equal to 4, I'm at 50 meters. And then so over here, from 4 to 6, let's say, I'm stationary. I stop. And then again from 6 to 10, I cover 50 meters. So the graph of the distance covered looks something like this. Right. So you could say the average speed was, so this is, let's say, distance as a function of time. Or if you are comfortable with just f of t, f is distance. Let's call it that. So at the end of 10 seconds, I'm at 100. Over here, I was at 50. So what does it mean to say, what was my speed at t is equal to 5?
That is
No, just look at the graph. Look at what I've explained. I started at t is equal to 0 with some speed. I reached 50 meters at t equal to 4. I stayed there for 2 seconds. And then once again, I accelerated and went up to 100 in another 4 seconds from t is equal to 6 to t is equal to 10. So if I were to tell you,
okay.
so what has happened between 4 and 6? Has my distance changed?
No, sir.
So what does that mean? That means I'm stationary, right? What would my speed at t is equal to 5 be?
0.
So from the graph, it is clear that this is 0. But just from this, it would not be clear. This story, this is just a starting and ending point story. But if I look at the graph, I do get to know that from 4 to 6, there is no change in my distance. Hence, my movement is 0, my speed is 0. But if I were to calculate using some distance by time, how would I do? So I would look at, let's say, average speed between 5 to 7. So what is my distance at 5? It's exactly 50. And at 7, it is somewhere over here. It is something like, let's say, we want 50, 25, let's say 62.5. I'm just giving some number. So suppose at this thing is equal to 7, I'm at 62.5. So between t is equal to 5 and t is equal to 7, what is my average speed?
62 minus 50.
So it's like 12.5 divided by 2. So that is just f of 7 minus f of 5 divided by 2. But that doesn't give a good estimator. So this is something like 6.25, right? But 6.25 is actually not my speed, even though my average over the next 2 seconds was 6.25. That is not the instantaneous speed. The instantaneous speed, as we noticed, was 0. So I take a smaller interval. I just look at 5 to 6. What is f of 5? I was at distance 50. F of 6 is also 50. So what is the average speed from
50 minus 50 by 1.
So here you get the
0.
average speed equal to 0 itself. But still, this in general may not be indicative of what instantaneous speed is. So in order to get instantaneous speed, what should I do? I should look at something like, if I'm looking at instantaneous speed at t is equal to t naught, I'll take some step further, and then I'll do this. So what is this measuring? This is measuring the distance that I traveled from the
Incremental
time t
input.
naught to t naught plus h. Now, if I divide it by the time difference, that is just h, right? This would be the average speed. Average speed from t naught to t naught plus h. Is this clear?
Yes, sir.
Now, if I can take the limit of that as h goes to 0, what would happen? I'm shrinking the interval in which I'm going from t naught. So just like I started with 5 to 7, 5 to 6, I can do 5 to 5.5, 5 to 5.4, smaller and smaller. That limiting value is what we call instantaneous speed. Is that clear?
Okay, sir. Sir, here in this example you have taken, that is the limiting value. I mean,
The
like
limiting
we
value
will.
was achieved within 1 second itself, but that need not be the case usually.
Okay, sir.
All right. We'll see examples of that also. Okay. And this is the right time to give the definition of a derivative. F from D to R, A belongs to D contains an interval containing A. Don't worry too much about this condition. So you should not have something like A to 3, B, whatever. You should not have stuff like this. It should be an interior point. There should be an interval containing A within D. So it should be an interior point. It can't be a corner point, end point. Contains an interval containing A. if limit as x goes to a f of x goes to a, h goes to 0, f of a plus h minus f of a divided by h exists, then f is said to be differentiable at a, and the limit is called the derivative. So what you need to remember is this limit, but you don't need to memorize what limit you are calculating of. It is very intuitive, very natural. What you're looking at is rate of change. What is rate of change? Rate of change is nothing but change in output divided by change in input. Now your function need not just be the distance function. You could have any function, and this would still make sense, right? So if I have some function whose graph is something like this, I want to look at the rate of change at, let's say, this point. Let's say this is x naught, and I take some x naught plus h. As I go from x naught to x naught plus h, what is the change in the output? That would be f of x naught. Okay, we have used a, so let's continue using a plus h. What is the change in output? F of a plus h minus f of a. What is the change in input? We have gone from a plus h to a plus h minus a, which is just h. And I want to take smaller and smaller such changes. It could be on this side also. It could be this way or this way. So we take the limit as h goes to 0. So this is how you need to think of it. And so the limiting value of change in input by change in output is the instantaneous rate of change. Does this make sense?
Yes, sir.
Right. So let's do one example by a couple of examples, maybe by first principle. So computing the derivative this way is called doing it by first principles. So let's do a couple of examples. What is derivative of x squared? F of x is equal to x squared. First, let's do x, no? Then we'll do x squared. You already know this at x is equal to a. So what would this be? Limit as h goes to 0. The limit that I have to calculate is that of a plus h minus f of a divided by h. So limit as h goes to 0 of
That is a plus h.
if I simplify this, just becomes 1. The h in the numerator and the h in the denominator get cancelled out with each other, and what you are left with is just 1. And you know this, right? You know that f prime d by dx of x is just maybe here I mentioned that notation. You either write f prime x or you write d by dx of f of x, and with lesser brackets most of the time. Using this and the rules of derivatives, which I'll state, you can do any x to the n, any polynomial, and so on. But something else. Let's do derivative of x is equal to e to the x at x equal to. So here, what is the limit that you have to calculate of? It goes to 0. F of x plus h or a plus h minus f of a divided by h. Now, what is this? I can take this as a common thing. And this doesn't have any h term. So this just comes out because scalar multiple of the limit of the scalar multiple of something with a function is scalar multiple of the limit. So I can just bring that out. But then you remember that we said that this thing is equal to 1. E to the x minus 1 by x. So this is just times 1, which is e to the a. Before going into the properties of products, let's do derivative of, let's call this 1, 2, 3. The derivative of f of x is equal to x square just by first principles at x equal to a as usual. So this would be f of a plus h minus f of a divided by h. But in this case, what is f of a plus h?
A plus h the whole square.
So it's a plus h to the whole square minus f of a is just a square divided by h. If I simplify further, what is a square minus b square in this? Okay, well, something square minus something square, it would be this plus a into this minus a divided by h. So you have an h which gets cancelled with a thing in the denominator. And what is the limiting value of the numerator, the part that's left in the numerator?
Sir, that is 2a plus h. If h tends to 0, then that would become 2a.
And this is something you know,
What?
right? Is there any doubt?
No, sir.
You know that the derivative of x square is 2x. At a, it will be 2a. So this is one way to derive it. Right, so you could do sin x also. I'll leave it to you. For sin x, you'll get some term of the form sin of a plus h minus sin of a divided by h. And at this point, what would you do?
Sir, we can find the value of
Sin
sin
A
a
plus
plus
B.
h.
You
Yes.
can write it as sin a cos b plus cos a sin b, and you'll get a term of the form sin h by h, and then you'll have something of the form cos h by h also.
Yes, sir.
Cos h this one, and sin cos h.
Sir, cos h will
Yes,
become 1, right? If h tends to 0.
yes, yes. Contacts and I don't know the most. Anyway, we'll not go into that. This also can be done. Sin times cos h minus 1. Yeah, even that can be simplified. You'll get an h in the numerator. Okay, if there is time, we'll come to this at the end using first principles. Does everyone know the derivatives of standard functions? So by standard functions, I know I'm going to list some of them. Maybe I'm not covering everything. Standard derivatives. By standard derivatives, I mean derivatives of standard functions. So for example, d by dx of x to the n is nx to the n minus 1. Then trigonometric functions, I'll just write sine and cos. And what else do we have? Well, there are other trigonometric functions, but they can all be derived from this and the properties of derivatives that I'll state. And then d by dx of e to the x we have already seen is e to the x itself. And d by dx of log x is 1 by x. And then what else is there? Exponential, let's give the general one also. D by dx of a to the x. Does anyone know what this is?
A to the power x into ln a.
Natural logarithm of a. Well, then there is inverse trigonometric functions and stuff. Refer to any standard list, you will get more. Mostly you will be needing only this and the properties of derivatives. Once again, we have f, g, from d to r. A is a point in that, let's just say f prime a, g prime a exist. Then first one is that f plus g prime a is f prime a plus g prime a. The sum behaves in a way that you normally expect. Similarly, if I have a scalar, then the scalar multiple of a function, the derivative of that is equal to the scalar multiple of the derivative of the function. That's another rule. And the product rule is where things are slightly different. So you have f of a g prime a plus prime a g of a. And all of these also I'll be very quickly going through. I hope all of you are familiar with this. If you are not, you have to speak out. This is f prime a g a minus f of a g prime a divided by g of a square. As usual, we'll say g of a is not equal to 0. Is there any other? Yeah, composition is also important. So if I have the composite function f of g, now the composite need not be well defined. We are assuming for this rule that is in the case that it is well defined, then you will have this to be f prime g of a times g prime a. The composition rule, as it is stated, may not be easy to see, but what you're doing is, I think you have already done examples of this sort. Let's take some simple example. Tan of x squared. Let's say something like this. So how would you differentiate this? First of all, let's do tan x. We have not, in the standard rules, we have just said sin x and cos x. But using sin x and cos x, can I do tan x?
Yes, sir.
So this is sin x by cosine x. So f prime x by the quotient rule, it would be cos square x, cos x into d by dx of sin x minus sin x into d by dx of cos x, which when I simplify becomes cos square x plus sin square x divided by cos square x. This is secant square x. Now that I know what that is, let's take up tan of x square. And let's take up tan x square. So can I write this as, let's say, g2 of h2 of x? So if I want to write this as a composite function, first function is h2 of x, and then that is taken as the input for g2. What are g2 and h2? Can you tell me?
G2 is tan of x and h2 is x square.
h2 is x square. So what I'm essentially doing is, let's say all of these are on R, or wherever tan does not go to infinity. I'm starting out with a point x. I'm mapping it to the point x square, and then I'm taking that as the input, and then I'm mapping it to tan of that. So if my g2 is equal to just, sorry, the first one is h2. h2 is the square function, and g2 is the tan function. If I start out with x, I go to x square, then I go to tan of x square. So this is what composition means. What does the composite rule say? G2 of h2 prime at x is g2 prime at h2 of x times h2 prime of x. Now, what is the derivative of g2? That is secant square x, right? It is g2 is tan x, so g2 prime is secant square x. But here we want not secant square x, but secant square h2 of x, because we want g2 prime of h2 of x times h2 prime. h2 is x square, so for this I know that this is 2x. The derivative is 2x. So yeah, secant square of h2 of x is this times 2x. You might have studied this as, when you have tan of something, you just don't look at what that thing is, just differentiate it as just the tan function, right? Whatever is inside as it is, and then differentiate whatever is inside. It is basically the same thing. So what does this rule say? You first differentiate the function, not looking at what the input variable is lived as it is, and then differentiate this. So for example, what would be the derivative of e to the ax?
A into e to the power
A.
ax.
So it is the differential of e to the x, which is just e to the x, but it's not x, it is ax. And then I differentiate ax, which gives me a. So that is e to the ax. So similarly, but the order in which the composition is being done is also important. So can you write this as a composite of two functions?
Yes, sir.
Can you tell me how?
Sir, maybe we can take the inner function as tan x and the outer function as x square.
So does this work?
Yes.
So we already have the functions, but they're just in the reverse order. I start out with a function, I start out with the variable x. First, I apply g2, which is tan of x. So then I take tan of x as the input for h2, which is squaring whatever the input is. So I get tan of x, the whole square. So in this case, the derivative of f would be h2 prime g2 of x times g2 prime of x. H2 prime is just 2x, but here it will be 2g2x. I'm going to skip a few steps and just write it as 2 tan x times g2 prime. G2 prime is secant square of x. So of course, when you're composing two functions, the order matters, and you'll get different results. And if you are familiar with your older thing, you forget what this is. Just it is the square of something, right? It has 2 times that, and then differentiate that. Whichever way you want to remember it is okay. It's the same. All of these rules, of course, you can apply whenever the limits exist. If you don't even know the limit exists, once again, as in the case of limits, where we said that we don't know the components have the limit, then you can't take the limit of the product. Similarly, you can't say the product of this thing is equal to this expression, for instance, if we don't know the existence of either of the limits. So this will help you solve mostly all problems. This set of properties along with the standard. Here you don't even need the n to be an integer. Even for non-integer it works. But yeah, for negative stuff you need to make sure that x is positive. Uh, yeah, x is positive so that you don't have an issue with negative square roots, square root of negative number and so on. Right. So we maybe have to go to L'Hopital now. Or is there? Yeah, maybe I'll give you an example of function which does require good use of first principles. Right? Take this as an exercise and try to tell me if the derivative of this exists, and if it does, what is its value? Take a couple of minutes.
So to check
Is
the derivative,
is f
if
differentiable at x equal to 0? If yes, what is f prime 0?
sir, uh,
Yeah,
sir, if a function is not continuous, then it won't be differentiable, right?
yes, that is also one thing.
Okay, so we can check the continuity if our claim is that it is not differentiable, right?
But is this not continuous?
It is continuous actually. Okay, sir. If that is
Yeah,
continuous, then
that's
we need to check, right? That is
yes.
differentiable.
If it is discontinuous, then you don't need to even check. Then you can just say it's not differentiable. I'll make that remark after this example.
Okay, sir.
X is equal to 0. Differentiable and continuous.
The limit doesn't exist actually.
Okay. One answer is, so you're saying f is not differentiable, right? Is there anyone who claims it is differentiable?
Sir, I guess it will be differentiable. I just
Wait,
want to
you
check.
just said it is.
I got LHL and RHL is equal to 0, which is fx x0. So
So that's for continuity, but here we are asking differentiability, right?
Yes, sir.
it's differentiable. Should be-
Sir, it will be differentiable according to me. I just want to change
It is
that.
differentiable. So
Okay. Is there anyone who says it's not differentiable? Is everyone convinced it is differentiable? Shall I move on to the next example? If you guys are not getting, you need to say that we need more explanation. Okay. How did you say that it is differentiable?
Sir, we can apply the first principle here. So that would, after applying that, we'll be getting h square into sine 1 by h minus f of 0, that is 0, divided by h. So we can cancel one h, then we'll be getting h into sine 1 by h. So by applying the sandwich principle, we can say that that will be 0.
Okay. I hear you. So what if I do this? So I know that the function is given by x square sine 1 by x at points other than 0. So I use the product rule. I say it is x square times sine 1 by x, the derivative of this, plus the derivative of x square times sine 1 by x. Okay, so this is just product rule. And then now I have to use the composition rule. Cos of 1 by x times minus 1 by x square plus 2x sine 1 by x. My x square get cancelled and I'll be left with minus cos 1 by x plus 2x sine 1 by x. And this does not converge as x goes to 0. Right? If I put x equal to 0, then I will not get, this term will cause a problem, cos 1 by x. So can I say f is not
Yes.
differentiable?
No, sir.
So what is it that I'm doing wrong?
Then maybe like applying the first principle, in this way, finding the derivative may not be useful always.
Yeah, so it's not just it's not useful. This is the wrong way to do it. Like you're differentiating the function at points other than 0 and then applying 0. That does not work. So all these rules and all that you can apply only when you know when it is differentiable. So this is wrong. This approach is wrong, but unfortunately it is common. When you have a function that is defined one way at different at points other than the given point, and then at the point it is defined in a certain way, you have to always revert to first principle. You can never go wrong with the first principle. So what does the first principle say? I need to look at the following limit. And I think this is what you were explaining earlier, and you were explaining it correctly. I'll just write it down for the clarity of everyone else. What is f of 0 plus h? That would just be h square sine 1 by h. And what is f of 0? F of 0 is given to be 0 divided by h, and one h gets cancelled, and what is remaining is h sine 1 by h. And we have already seen this, right? When I was explaining the applications of the sandwich lemma, we saw that this is equal to 0. So the limit of this ratio of change of the function with respect to the input exists and is equal to 0. So f prime 0 is equal to 0. Is this okay?
Yes, sir.
You should not do this. All right. You can't just look at the expression there, x square sine 1 by x, and then just differentiate it. So exercise, what about, well, at this point you should know, what about just x sine 1 by x? X not equal to 0 and 0, x is equal to 0. Can you guess?
Sir, this is not differentiable. We cannot find the limit of sine 1 by h.
So answer is f is continuous, as we have seen earlier, but not differentiable. So you can have functions which are continuous and not differentiable. We have seen simpler examples also, like mod x and so on. But the result which will help you eliminate, or which will help you conclude non-differentiability is the form. F is differentiable at a point. I'll not keep writing at a point. Implies f is continuous at that point. So there is no way for a function to be discontinuous but differentiable. That cannot happen. So if you look at some function, if I give the same example, but with a little twist, that x square sine 1 by x and 1 instead of 0. Is this function differentiable?
This is not even continuous. So
Yeah, so this is not continuous. So immediately I can conclude that this is not differentiable. So another way to write the result is f is not continuous implies f is not differentiable. Okay, this example, this exercise, solve it. It will go back to one more problem that we have already discussed in the past. Now, L'Hopital's rule. So if you have to compute the limit of something, it's okay. Want to compute limit as x goes to a f of x by g of x and one of the following is true. Okay? Well, when you're doing problems, it will be much easier than if I write it precisely. Prime limit as x goes to a of x is equal to 0 and limit as x goes to a g of x is equal to 0 or limit as x goes to a f of x is infinity. It could be minus infinity also. And by infinity, I just mean one of the two. So you have a ratio of two functions, both of which go to 0 or both of which go to infinity, plus or minus infinity. So in such a case, and also suppose the following is true. You need some conditions which for most of the examples that you're dealing with will be very straightforward to check, but I will just list it for clarity. What you need is f prime x and g prime x exist. There is clause which says except possibly at a, that I'm not. Refer to the props videos for an even more rigorous version of this in a neighborhood. So if you just say g prime a is not equal to 0, it could be 0. I just need it to be this. Bear with me for a bit as I write this down. Then I'll explain with examples and it will be clear. Then limit as x goes to a f of x by g of x is equal to l. So what's happening? So here, despite all these technical conditions, what is happening is you have a function which is the ratio of two functions, both of which go to 0 or both of which go to infinity. But the derivative of both the numerator and the denominator exists in a neighborhood of the point of interest. The denominator is not 0. The derivative of the denominator is also not 0. Then what you can do is individually differentiate the numerator and the denominator. And if the limit of the ratio of the derivatives exists, then that is equal to the original limit. We will do it with examples. This was one of the limits that I said needs to be memorized. So does this satisfy all the conditions? I am given a function which is written as a ratio of two functions. Yes. What is the limit of the numerator?
0.
And what is the limit of the denominator?
Same 0.
So this is in a 0 by 0 form. So that is okay. And these are trigonometric or polynomial functions. So the derivatives exist. The derivative of the denominator is never 0. All of this is true. What can you say about limit as x goes to 0 d by dx of log 1 by x divided by d by dx of x? So what is the numerator now?
1
Limit as x
by
goes to 0.
1 plus x.
This is just 1 by 1 plus x. Because even if you do the composition rule, you will be times 1. Check this. And this will, the denominator is just derivative of the function x, which is 1. Now, if I just rewrite it, I'll be left with only this. And what is this limit?
1 only.
1. So that I can get directly by substituting. Initially, I could not directly substitute because I would get a 0 by 0 form. Instead, what I did was I differentiated both the numerator and the denominator. And note that you can do this only when you have a 0 by 0 or an infinity by infinity sort of function given to you. And if the resultant fraction after you differentiate has the limit to exist, then that limit will be equal to the original limit. So this is equal to 1. Can you try limit as x goes to 0? Okay, here it's again. If I don't specify the base, it is natural number. So can you use the product rule for this?
Sir, product rule meaning like here, what is the question?
What is the limit
derivative.
of this is what I'm asking.
Okay.
So it's the product of two functions. So can I use the product rule for limits?
Sir, the x function that will go to 0 and ln x will go to infinity, I guess.
Negative infinity, but okay, yeah. But okay, this limit does make sense because we don't have the negative side of thing in the domain. So let's have it as 0 plus. You can do the same L'Hopital's rule for one-sided limits also. That is what we are doing over here. But okay. Now, how can I use L'Hopital's rule for this? Can I use L'Hopital's rule for this?
Sir, this is not in the form 0 by 0 or infinity by infinity.
But can I transform it into the can I transform
1
it to
by
that form?
x, 1 by x, the denominator.
Can you tell me how to transform it into that? Anyone?
Can we
What about,
choose something there?
can I do this?
Oh, yes, sir. Yes.
So sometimes it is not directly given in a f by g type of form, but 0 times infinity. So this is 0 into infinity, right? So 0 into infinity is just infinity by infinity in disguise, or 0 by 0 if you want to go that way, but it's better to keep log in the numerator. Now, can I use L'Hopital's rule? Let's see. What is the derivative of the numerator?
1 by x
And what is the derivative of the denominator?
minus 1 by x square.
So if I simplify, what will I be left with?
X only. Minus x.
And what is this?
0.
So here, the function x is becoming smaller and smaller in value, and log is going arbitrarily negative. So it's not clear what the product will behave like. But as it turns out here, it actually goes to 0 itself. All right. So sometimes you'll have to transform the problem into a more recognizable form. solve the
Sir,
problem.
if this thing doesn't come to our mind, then can we apply the first principle?
You can, but I think here it would be difficult.
Okay.
X log x, how would you do? You would take something like, but then here you're just computing the limit. Now you don't know the function value at that point. Here you're not computing the derivative of this. I'm not even asking if the derivative of this exists. We are just at a limit level.
Okay, sir. Okay.
Right. So here there is,
Derivative because 0 is not in the domain here.
yes, 0 is not in the domain unless you want to define it as something like 0, if you want to. Then you could, but then 0 is not in the interior of the domain. So differentiability at 0 doesn't make sense.
Okay,
It's a
sir.
corner point of the domain, even if you define it as something specifically at 0.
Okay,
So
sir.
here
And
differentiability
sir,
doesn't make sense. Yeah.
okay, sir. And sir, you just before some time you defined that if we'll be getting some 0 into infinity form, then we can convert that into infinity by infinity form, right? So,
Yes.
so 0 into infinity, that is some kind of indeterminate form, right?
0 into infinity is also an indeterminate form. Yes.
Okay. And sir, I have seen some questions which is in the form infinity minus infinity. So can we convert that into this 0 by 0 or infinity by infinity form?
There might not be something that works for everything, but infinity minus infinity is also an indeterminate form. You
Okay.
have to
In that
simplify it
case,
some.
okay,
There
sir.
is no direct way to apply L'Hopital's rule. Oh, here at least I can say that if it is 0 times infinity, then if this is the part, if f is the part that goes to 0, then this would be infinity by infinity, right?
Yes, sir.
Or if it is easier to calculate the derivative of 1 by g, you would write this as 0 by 0.
Okay,
For
sir.
the difference, I can't think of anything immediately that would work every time. I
Can we
doubt there is any
apply
rule.
this thing there, L'Hopital rule?
If you can bring it to a 0 by 0 or infinity by infinity form, then yes. So here,
Okay.
as it is, it says only if it is 0 by 0 or infinity by infinity form.
Yes, sir. Okay.
First one. Same course. Yeah, no, not sure if there is anything that would always work. In specific examples, maybe you can.
Okay, sir.
So if you have something like 1 by x minus 1 by x squared, you can write it as x minus 1 by x squared. But this is not, so this is infinity by minus infinity, right? As limit as x goes to 0. If I simplify it, then it becomes
So that
x
is
minus 1 by x
x
squared.
x whole into x minus 1, right? Divided by x square. Then this square will vanish.
No, what? I didn't get what you're saying.
So this is x square minus x divided by x square.
Why x squared minus x? If you do x squared minus x, then you'll get an x cube. If you just do cross multiplication.
Sir, the result of 1 by x minus 1 by x square will be x square minus x divided by x. Acha, okay, sir. I got confused.
Yeah.
It is my fault. Okay.
Yeah. So here the limit doesn't exist. This is not a 0 by 0 form. This is a minus 1 by 0 form, which will go to infinity. Right. So
Oh,
this
okay.
thing is going to a finite value. This is going to 0. So the ratio will go to infinity. negative infinity to be more precise. Not always. So this is just an example to demonstrate not always minus infinity by infinity minus infinity will not always convert to a 0 by 0 form. Okay. So let's get the last part done quickly. As an exercise, you can take this, prove all these things that I said that I'll come back to this. Are all of these solvable just by the rule now? Can you quickly scan through them and verify that all of these things are not something that you need to memorize anymore? Do you see it?
Yes, sir. All of this can be done using L'Hopital rule.
Yes. Now, going back to that figure that we were drawing earlier, consider a function which is differentiable. There are no corners and so on. And what is the tangent to this? There were many arbitrary definitions, not arbitrary, but somewhat intuitive definitions that we said it should be just touching the curve at that point and so on. So now we'll make that slightly more rigorous. In the same sense that we have been working, we'll look at things like x naught and x naught plus h. In order to compute the derivative, we looked at these two quantities, took the difference of the function value and divided by the difference of the input value, and then we made h smaller and smaller. We went closer and closer to the point of interest x naught, and then looked at the ratio and called it the derivative. Now, what I will do is look at these 2 points, x naught, f of x naught, and x naught plus h, f of x naught plus h. Just look at the function at these 2 points. So basically, I'm looking at these 2 points and look at the line joining them. The line joining, let me call this point P0 and PH. P0 and PH is called a secant at x. Now, what happens to this line as I come closer and closer to, so once again, rough graph. So this is one of the lines. Does the direction of the line give me the direction of the graph at this point?
No, sir.
Not exactly. So I go closer. I take this point. Does this give me the direction of the graph?
No, but some
It's
more
better,
close.
right?
Yes, sir.
Yeah, it's better only because here we don't have many oscillations. If it has many oscillations, it also need not be better. But you get the idea, right? So what I do is take closer and closer secants. Secants defined by closer and closer points. I get a better sense of what the direction of the graph is at that point. So is it not natural to say that the tangent line at x naught is the limit? I've said limits of functions, I've not said limits of lines. So I'm just going to put it in quotes. It's the limit of secant lines as we approach x. Does this make sense? It's not a rigorous definition. Once again, if I go closer and closer, and at the end point, if I just am there, I'm just there, the limiting secant is what we call the tangent. Does that make sense?
Yes, sir.
Okay. Now I want to find the equation of this tangent line. So what is the slope of the secant line? So if I look at this as per earlier definition, P0 to PH, what was the slope of the secant line?
That is f of a naught plus h minus f of a.
So I have these 2 points, right? So if I have 2 points, we can compute the slope of the line joining the 2 points. What is that? If I have
F
x1,
of
y1, x2, y2. Yeah, go ahead.
f of x naught plus h minus f of x naught divided by x naught plus h minus x naught. That is h.
So does this look familiar?
Yes, sir. If h is tending to 0, then it would be the derivative.
So this is the slope. Sorry, h. This is the slope of the secant. So what is the equation of the secant? Equation of the line in a, you know that it passes through x naught f of x naught. Every secant passes through this point, so we'll use this point. I could use the other point also, doesn't make a difference. Equation of the secant is y minus y1, which is f of x naught, is equal to m times x minus x1. This is the equation of the secant for value h. Is this fine?
Yes, sir.
Now, I've said that the tangent is the limit of the secant. So one way to properly write that is the slope of the tangent will be the limiting value of the slope of the secant. So what is the slope of the tangent then? The limiting value as we approach the point of the slope of the secant.
This part I didn't got. Slope of the tangent is.
Okay, so suppose I'll draw a simpler graph and I'm trying to look at what the slope of the point at this, slope of the function at this point is. So intuitively, what is the tangent to this? It is the horizontal line, right? And the curve is flattening. At this point, it's actually flat. The direction of the graph is horizontal. So if I take a secant, it will not give me the slope of that and this are different. But if I take gradually closer and closer points, and so this is my L1, L2, and I can take closer and closer points and corresponding secants. What happens is I go closer and closer to the tangent. The
That
tangent,
will become the tangent.
in the limiting case, it will become the tangent. The examples that we have taken are simple enough that the limiting case is actually realized, as in you can just look at that thing. But if you want to know what the slope of the tangent is, you look at the slope of this L1, you look at the slope of this L2, and then you go closer and closer. The limit of those slopes are the limit of the tangent. See, ultimately I want to write the equation of the tangent line. I know that the tangent line passes through x naught comma f of x naught. So I want it in the point slope form. So if I get the slope, I'm done. So with the understanding that the tangent is the limiting case of the secants, I will say that the slope of the tangent is the limiting value of the slope of the secant. And the slope of the secant was calculated simply using coordinate geometry, the slope of the line, the standard form of the slope of the line joining 2 points, all of these things is like week 1, week 2 content, which you're already familiar with. But what is new is, the limit of this also. What is the limit of that ratio?
So that is, so for this graph,
No. What is this? How do I simplify this?
oh, this is the derivative, sir.
So this is just f prime x. So one way to define the tangent of the tangent line of a differentiable function is it is the line that passes through the graph at that point with slope equal to the derivative at that point. So all of this is just for you to visualize things better. What you really need is equation of tangent line f at x naught, meaning that at the point x naught comma f of x naught, this is given by y is equal to f of x naught plus f prime at x naught times x minus x. This is just y minus y1 is equal to m times x minus x1, which is the
Is it
equation of the
safe
line
to-
and the point slope.
Is it
Sorry?
safe to say, like at this point, the second line is like becoming the tangent line?
Yes, that is how you visualize it. For example, if you have something like x square sine 1 by x, you can't always and 0. We saw that this is differentiable, right? With slope equal to 0. So its graph will be something like this is just guidelines. Okay, it'll go like this, something like that. You can try to draw the graph of it. You'll see that it will be restricted within those two things, and you can't really see it always. If you have a very nice f of x is equal to x square, you can see that the secant line is actually becoming the tangent line. But the visualization is not always obvious. Functions can be very wide. Most of the time we deal with nice enough functions, and for the kind of functions that you'll be dealing with practically, it'll not be a problem. The derivative will be straightforward enough to compute. These are more like mathematical curiosity extreme examples, which may not be very relevant to you, but I'm just telling you these things so that you can see things better. All right. So that's the equation of the tangent line. This also happens to be, so put this in a box, important stuff. And then there is the concept of linear approximation. Now, if I take that equation of that line and just write it as write this function. This is a function in x. It is of the form just a plus bx, or if you rearrange it, it will be of the form a plus bx. So this is a linear function. And of course, we have taken the equation of the line, right? So if you have some graph and at some point, you are drawing some line. Now, if you compare the graph and the line, the closer you go to the point, the better this approximation is. So linear functions behave very well, and for computations, it will be very useful. If you have some logarithmic exponential function, that may not be very easy to compute, especially when you have a lot of data and all that. So sometimes it is better to use a linear function in place of the original function. The original function may be very wide, but a linear function usually behaves well and has far fewer parameters. So what is a good function to use in place of the given function? There are various degrees of approximation. Linear approximation means you say which is the best straight line which would approximate the behavior of the function near that point. So that is given by this function, which is called the linear approximation of f. You should understand it as this is a linear function which best mimics the behavior of f close to x naught. So if you look at farther points, the difference is huge. Only close to x naught you have good behavior. So this is good approximation of f near x naught. What near means to what extent you want this to, the degree of accuracy and all that. Those are finer points. But for now, you just know that this is the linear approximation, and why it is used is because near the function, they are very close. And if you have the function to be linear to begin with, if this was your f of x, what do you think the linear approximation of this will be?
That same line f of x.
It should be the same line. If you have a linear function itself, its linear approximation will be itself.
So positive negative will be matter. Means here it is going minus infinity. That one is going positive infinity.
No, that depends on what the value of f prime x is. Right? It could be flat also. It could be horizontal also. So if I look at this point, for instance, here f prime x will be 0, and you will get the tangent line to be flat. So the sign of the derivative will say whether the function is decreasing or increasing, or it's a critical point if you have seen these things before. And the tangent line will also behave in the same way near the point. So if f prime x is negative, that means the slope of your line is negative. The function is decreasing, and that is visible by the linear approximation also. So similarly, if you have a positive slope function, at that point, if you have a positive slope, your tangent will also have positive slope, and it agrees. It is consistent with the notion that the function is also increasing at that point. Does that answer your question? Okay. All right, this is where we'll stop. And if you have any doubts, we can take it up quickly if there are any doubts. Ideally, you should do examples for these also. But you have
Session
another session
recording will be
tomorrow.
available, sir.
YouTube has the records of all the IIT MBA's degree program. YouTube channel has a playlist for Math 1, which will have all these things.
Okay, sir.
And-
Thank you so much. Good night.
And notes will be uploaded, and the sheet for the notes also has been shared. It's on Discourse as well as in the portal. In supplementary contents, you'll get the notes. All right. If there are no more doubts, let's wrap up.
Thank you, sir.
Okay, sir. Thank you.